such fake public service announcements as, help, my EIP's out of control, and the heaping you, and irrespective. But today I decided to take the X-Force cape and utility belt off and come here to talk to you about a very important issue, NX. So if you don't know what NX is, it basically stands for no execute, and it's a generic way to do buffer overflow protection. I'm treating this as if it were a blind date, because I think that's the most awkward situation when you get to know someone, and that's kind of how I feel about this subject. Start from the beginning. What is the problem? Everybody here should know what buffer overflow is. Why it's important. They're used heavily in exploits, worms. Everybody basically is starting to know, what an exploit is. Even, non-technical people. My parents, for instance, know what buffer overflow is. And the terms root and own are becoming more used in, common vernacular. Everybody now knows, of course, about Microsoft Super Tuesday as well. I mean, the releasing of security patches has become, part of common culture. It's getting more important. Computer security is no longer a movie subplot. It affects people where it's most noticeable, the wallet. And as you've noticed, I guess in the last couple of years, there's been more and more talks about worms costing people money, people losing credit card numbers, information like that. So computer security is becoming more and more important. For instance, the worm stop ATM machine from working. Everybody remembers that from the Blaster exploit. Was anybody here affected by that? I was. I couldn't get money out of an ATM. That was great. Worms cost up to $50 billion. Somewhere somebody has got to be really proud of that a worm they wrote is costing somebody $50 billion. Of course, that's not a concrete number, but it's still reported. And this is a generic buffer overflow. I thought for the people in the audience that has never seen a buffer overflow, this is the most generic buffer overflow I could come up with. It's a snippet of C code. You take in the command line arguments. You pass the first command line argument directly to a function named Bob. Bob will then start copy that argument directly into a character array that's size of 5, and then print copy done and leave. So the problem with this is if you send in more, what happens if you send in more than 5 bytes? Well, bad things happen. Things get overwritten, and then the party starts. And this is one of the reasons a lot of work has been done lately to mitigate the coding errors that cause things like that. But this problem can be tackled from another angle as well, which is a hardware base. One of the reasons this happens is hardware allows it to happen. What about buffer overflows are strange? Well, where the code is being executed from is very strange. Normally, readable and executable memory, writable and executable memory, you don't want to execute code from there. The fact that code is being executed from there is kind of strange. The fact that the return address changes for a stack overflow in the middle of a function call, that's kind of strange. Some of these you're calling strange function calls that this program generally does not need. Basically, there's executable code on a stack or heap. There's a minor exception with that. Dynamically generated code like Java will run from generally run from heap space, or Packer's copyright protection stuff will do that as well. But these things are all kind of strange, and these are things that hardware makers feel that they can help you mitigate. So that has a problem. That raises the question: is buffer overflows a hardware or software problem? Hardware. A lot of this has to do with the hardware. What is NX? NX is a bit in the page table of certain microprocessors. It's the last bit in the page table. And if it's set to 0, the memory is executable. If it's set to 1, it's not. The page table must be in PAE format. The ability to set read, write, execute page permissions has been around since the 386 chip. It's just been never used. But basically, they've had the ability to stop executable memory, to stop this problem since the 386. But nobody's really been paying attention to those flags. By setting pages that contain no executable code to not executable, code injection exploits like stack or heap-based overflows can be stopped. Intel calls their own version of this XD. It's identical to what AMD is doing, except for the name. You gotta love how different vendors have to have different names for stuff. They just can't call it the same thing. Like the MX and 3D Now stuff from a couple of years ago. Same thing. You may see that NX is referred to as EDP, or Enhanced Virus Protection, in the AMD docs. Where can you get no execute support? Well, basically right now you have to use one of the AMD Athlon or Opteron chips or one of the Intel J-series chips. Is no execute the magic bullet? No execute is not a standalone solution. It requires operating system support, and that should make my phone ring. That should give you a clue right there. It's not the solid solution people think it is. What happens when stuff tries to get executed? Well, the CPU will just generate an exception. It's up to the operating system to handle that exception. Is it evadable or otherwise beatable? I sure hope so. Otherwise, this talk won't be very interesting. What isn't the no execute technology? Although it's called EDP, it really doesn't deal with viruses, just the exploitation vector. And a lot of people have confused, a lot of people have talked about this. Viruses generally don't exploit buffer overflows to spread. Worms more likely do that. Viruses generally, are parasitic and they'll attach in other ways, but the EDP stuff really doesn't do much for viruses. I guess it's just a marketing term because more people know what viruses are. This technology is designed to detect and defeat buffer overflows. If your attack does something other than code injection, there's a great chance it will still work. For instance, one of the best ways to gain unauthorized access to a machine right now is via like a web app security hole. And this actually does absolutely nothing to mitigate that. This only handles memory corruption exploits. There's a lot more attacks than buffer overflows in the world. In fact, there's other things like format string attacks that still work quite well. This is not a wide-scale deployable solution. There are many problems with it. The just-in-time compiler and some copyrighted protection schemes will break if you use this. It's not like comprehensive. There's basically the biggest problem with most security tools is lack of coverage, and this is no different. The code coverage on this is not very good. What might you confuse with NX technology? One of the reasons I want to do this talk is a lot of people looked at the press that NX got last year, and they didn't quite understand what it was, they didn't quite know what was going on. And even me, as a researcher, had some troubles actually deciphering what exactly NX does, because NX gets rolled into other things like DEP from Microsoft, the data execution protection stuff. So I thought it would be interesting to talk about what it really isn't. Non-executable stack. It sounds very similar, but these are mostly seen on RISC chips that have their own versions of a no-execute bit. Most strictly associated with the set no-exec user stack argument found in the etc system file in Solaris. It's not an API hooker. A lot of people target generic buffer overflow solutions as an API hooker. Basically what those do is that they overwrite like a function prologue with a jump into a static analysis engine that would then determine if the call is malicious or not and take effect on that. And this also really isn't a heap or stack canary. Those are stack values that are put at certain locations in the stack or heap, and then check at periodic times to make sure they haven't changed or been overwritten. If all these methods of defeating buffer overflow technologies have flaws, what makes no execute technology so much better? Nothing. It has flaws just like all generic buffer overflow prevention systems. Surely everybody can't get it wrong. What's the problem? Well, the problem is no execute technology is just like all these other technologies with cuts. They just are trying to band-aid a problem when they should actually be trying to fix the initial problem. For instance, if you wanted to stop this car from crossing a bridge, now is a bad time to start working on it. And that's my problem with most buffer overflow protection programs. If by the time you start trying to stop a buffer overflow is to stop the shellcode from executing, you've already lost. The shellcode's already, you can find different methods to execute the shellcode. Pages and page tables and PTEs, page table entries. What is a page? Fixed amount of virtual memory that can be segmented and used for memory allocations purposes. It's one of the smallest chunks, basically, of memory on the x86 chips. There can be large and small pages. On the x86 chips, the small page is 4K and the large page is around 2 megs. Building blocks for all system memory, you know it. Since it's the smallest block that hardware protection can be applied to, it's a perfect place to implement no execute protection. Pages are either in a committed, reserved, or free state. Virtual alloc and virtual alloc EX are functions used to do commit and reserves manually. Pages can be locked into memory, and pages can be shared between the processes. Virtual memory layout for a process is stored in page tables. These are normally only modifiable by the kernel to keep a process from changing its own layout during runtime. Used for the transition of virtual memory into physical memory. What is a page table entry? This is what actually contains a virtual to physical page mapping memory. Each virtual address has one. There's a lot more to do with pages, but that's pretty much what you need to know for this talk. So how does this relate to NX and what NX does? Well, normal x86 PTEs are too small. It's one of the reasons why the hardware-based NX stuff isn't available in anything but 64-bit chips. The 32-bit chips don't have a page table entry long enough to support the extra bit. That's why you can use it in 32-bit mode with something called PAE, which is the physical address extension, which basically takes the virtual memory lookups from a double layer to a triple layer lookup, which gives them the ability to have a much larger page table. When the code attempts to execute a page marked no execute, the CPU raises an exception. The error code, or basically how this is handled, is dependent on the operating system. What happens after the exception is raised, OS dependent, the CPU does not enforce the no execute rule directly, which is kind of lame. How does the operating system decide what its code was data to mark properly? The loader. Anybody know what the loader is? It does what it's named. It loads things into memory. It's a binary loader. There's a problem though. Is if the loader doesn't set the execute permissions properly, you really have no protection. I have to digress for a second. Everybody sees the results, but exactly what is a loader and how do you care? Like its name implies, it loads things. It takes a binary and creates basically an executable process. On Windows, more than one image type is supported. In fact, on Windows, you can execute OS2 files. That's kind of interesting. POSIX files, Win16 files, MS-DOS, COM, and BAT files. The loader has a specific image to run for each one of these binaries. So basically, when you try to run an application, it's going to look at what type of application it is, to load the appropriate program to take care of it. And it starts a create process. And before we go into that, while going through a lot of NT-OS kernel code in IDA, I found that I couldn't actually find this on the internet anywhere, and these function prefixes were pretty useful for me. So basically, this is a list of all the internal functions, or all the functions I found basically, and what they mean. The ones that I mostly care about, the MM and MI, the memory management, memory internal. So basically, this is how the flow of the loader. Create process is called. That calls create process A, which in turn calls create process internal A, which then calls NT open file, which will open the binary and read it in. Then you call NT create section, which will actually create the section's memory. NT create section will in turn call MM create section, and it will call a couple of other functions. MI find section will be called, the MI insert section object will be called, the MI create image file map will be called. And one of the last things that MI create image file map will do is a call called MI get image protection. And that's what actually decides what the permissions will be set on the new process. So this means that if you're not using a standard Windows loader to load your binary, then you're not really getting the protection of NX. The initial permissions are not set on the pages correctly, NX is useless in Windows. Since the processor does not actually enforce NX all the time, executing code cannot be loaded properly. It basically opens you to buffer overflows. So one of the examples of this, I'd love to do a demo, but the machine I was using got shipped here, and it actually died in transit. So we can't actually do that, but I have pictures. Windows has a Cygwin install. I installed Cygwin on Windows with Service Pack 2. DEP, which is the Microsoft Data Execution Protection, was enabled for all programs. The thing to note is this is a 32-bit version of Windows XP on a 64-bit chip. This is kind of what it looks like when you're setting it up. This is the actual code that I ran. It was pretty much a generic example I showed you earlier. And it will stop it. The funny thing is, if you run the same code basically in Cygwin, Cygwin won't catch it. And that's because when Cygwin process loads the program to run, it does it differently than the way Windows does it. So you're not getting the same NX protection. Different loader, pages aren't marked correctly, and then different memory management being applied. No execute technology isn't extended to everything currently on Windows. The default settings for DEP, which is the Microsoft implementation of it, by default don't cover all programs, just essential Windows services. This really gives you a false sense of security. A lot of people I talk to want to buy 64-bit chips just because they'll never have another buffer overflow problem again. And that's just not true. Edge protection has to have OS support to work. It can be selectively enabled or disabled. And if you want, you can use a process called Virtual Protect for Windows to check to change individual protection. Depth in depth. DEP is more than just an MS implementation of it. It has two forms, which is hardware and software enforcement. It can be a bit confusing as to when you are and are not protected. Many features that have hardware protection and say what the OS is running with. You basically have to have PAE, you have to have a no execute enabled chip, you have to set basically a correct flag in the boot options. There's a lot of different things you have to do before you're actually protected. Hardware enforced depth. This is basically what we're mostly discussing. It requires no execute enable on the chip. Protection enforcement is done on a per virtual page process. It protects both 32-bit and 64-bit versions of the OS if the correct chip is used. 32-bit versions of the OS require PAE enabled. Protection is configurable via control panel and boot INI options. Software depth only attempts to detect buffer overflows. It attempts to detect basically stupid SEH tricks. It uses a thing called safe SEH, which is a destruction exception handler stuff. Before any exceptions run, safe SEH tries to make sure that the exception handler is valid. And it does that by trying to make sure it's not in, it says not in executable memory, but it's not actually in writable memory. It's processor independent. A lot of popular exploits use SEH tricks to get execution. However, a lot don't. Boot INI, you basically have to have, these are options you can pass in boot INI to set the different options. Opt-in means that cover system binaries only in programs that you specifically define. Opt-out, enable for all processes except for the ones you define. Always on covers everything, always off, turns stuff off completely. Microsoft maintains a list of software that DEP breaks. It breaks Java, most copyright protection tools, a lot of games. Basically, there's an application compatibility toolkit called Disable NX that you can use to test. There's also problems with device drivers. A lot of device drivers will break when you use this because a lot of device drivers use a lot of stack to execute code, and you can't do that anymore. So why is NX bad? Brand new for first time ever released, new day, exploitation technique. This is awesome. Return to libc. Has anyone ever seen it? No? Okay, that's great. I'm just kidding. But return to libc is one thing because right now there's not too many things that will do address randomization of DLLs on Windows. Return to libc still works. It's pretty old. It's the best target of return to libc attacks is virtual protect. At that point, you can change the permissions on an entire block of memory. They continue as normal. Chaining and return to libc attacks will work. It's complex, it's tedious, it's prone to failure. It's not very portable. Return to libc has a lot of problems. I don't particularly like it. And the biggest problem is it doesn't help with heap overflows. And most of the things that I exploit these days are heap overflows. This is where I would do the demo. Basically, you build a fake stack frame, and you do a return to virtual protect, which is going to change all the permissions on the page to writable and executable, and it will add a user. What is the difference? Memory protection change. Well, basically, this is the new stuff. What you can do, there's a couple of different problems with this. For instance, is anybody familiar with copy on write? What a copy on write is? All right, well, basically, DLLs are shared amongst all processes until there's a reason why it should have a localized copy. And once a DLL has its own localized copy, the initial setup protection on it is no longer valid, and everything's back to writable and executable. That's kind of funny. That's one of the ways I was planning on exploiting a heap-based overflow for you. Say again?
Should it be copying the NX bit as well when it makes a copy on write?
Yes, it should. The other way are a lot of loader stuff we already talked about. is a great, most of this actually isn't all that great without the demos, but the loader stuff is another great way. You can execute code arbitrarily without much problems, as long as it's not loaded by the Win32 loader. Writing code to find the differences. Basically, what you want to do is you want to take a look at what a process memory map looks like beforehand and afterwards. You can use virtual query to do that. Virtual query is a function call. It's a Windows function call. We'll basically query a memory space and return values to it. Basically an MBI structure, which is memory basic information. This is like a really quick snippet of code that I wrote basically to find all the executable permissions, all the pages in memory with executable permissions. The return values you're interested in are defined in winnt.h. It's basically 0x, it's basically those. The ideal value is 0x40, that's read, write, execute. If there are any pages that are still writable and executable, you can inject code into that address and execute. For example, it does 4K checks up to basically kernel space. This is where you would you'd see the demo. Does anybody have a question about that? Nobody? The demo would show actually a program that was that I wrote that had a generic heap-based overflow in it. I'd exploit that and get a shell on the machine, even with NX enabled. The problem that's being exploited in that case is the DLL. I'm going to inject code into a DLL space, and when I do basically when the copy on write is done, the NX permissions are no longer preserved, so I can then execute anything at will. There's an easier way to view all of the memory permissions. There's a program I use called PRC View that lets you look at all of them. This is basically what it looks like. As you can see, most of the memory space in this process is read-write only. Down at the bottom, you'll see a lot of execute-write copies. Code coverage, heap tricks, this is what I was just talking about, timing, and execution paths. There's more, we can talk about that later. This is the fake server demo. Linux supports NX. They've supported it since June 2004. Support was written by Maynor. You may remember him from such as his O1 scheduler. His works on RAID and wacky kernel stuff like kernel drivers that are FTP and HTTP servers. In case of Windows, Linux has prerequisites that you must have coverage for before the support will be active. They have a problem with code coverage as well. Basically, if stuff gets paged out and paged back in with kscand and BD flush, you're going to have problems with the NX stuff. What's needed to make Linux do the no executable dance? You need a CPU that supports NX, BitNX, PTE. You also need to compile it with PTU, GNU stack guard. This allows you to mark stacks as non-executable. Basically, you can use readelf to take a look and see if you're actually protected. If you're covered, you will see a message in your boot up, NX execute disable protection active. No execute support can be disabled by passing no execute equal off via the command line. This protection is included in most popular distributions. User line versus kernel space. The NX protection provides user line support. Kernel space overflows are also protected against. Many open source tools are not known to follow standards very well. In homegrown or custom built apps, stacks have to manually be marked as non-executable. Things that are dynamically generated at runtime will cause serious problems. Once again, just like Java. Once again, this is where I do a stack-based overflow. One of the funny things about 64-bit chips is everything's R instead of E. So it's RIP, RAX, RBX. It's kind of funny. And you basically at this point would run through the same thing. You'd use a function call to walk the entire memory map of a process and check what is and what is not marked as non-executable. Return to libc attacks still work on Linux. However, Linux has a lot of address randomization stuff in the libraries. So depending on the distribution, this is a lot less effective. What is actually done when the kernel catches something bad? Well, it'll do a print K, and then it will try to allow, or will try to decide if it should allow or disallow. Where do the page permissions get set? Same place, just like Windows, in the basically in the loader when it gets loaded. How does this affect a heap? Basically, heap-based overflows are kind of funny. Stack-based overflows require basically that once you overflow a stack, you overwrite the return address with the address of something that will basically correspond to something that will give you execution. The example is after you do a stack-based overflow, you want to make EIP return to something. Generally, I guess it would translate to jump ESP, which would be FFE4 in opcodes. So once it returns to libc and you hit FFE4, which is jump ESP, it will immediately jump to the stack and start executing your code. Heap overflows are a little bit different. Heap overflows will give you the ability to do an arbitrary overwrite, basically anywhere of 4 bytes. So heap overflows, NX won't actually stop a heap overflow from happening. What it tries to do is stop you from executing code with it. If you intend to do something with a heap overflow, like overwrite the UID of a currently running process or something like that, NX really isn't going to help you much. Dereferencing null pointers are kind of funny because it will cause an exception first. And if you have an exception race, strange things can happen in the Linux kernel. And this is where I would do the demo of owning Linux. I was thinking about this a lot. Things that kernel developers don't think about, but security researchers do. For instance, races for interrupts are one of those. But once again, I have to apologize because the demos aren't working today, but we're going to be releasing a white paper with all this information in it after the show, and it will have more detailed examples of all this. It's not the end-all be-all security solution. Major compatibility issues with existing code. You got code coverage problems, alternate flows of data. So basically, NX will work if you do something a certain way, and if you do something a different way, it won't work. It only helps with memory corruption bugs. For instance, a format string bug where you want to change your UID won't help you at all with that. Heap overflow where you want to do like a generic override of something, like a 32-bit value, it won't help you with that at all. It should not replace any current security tools, but it's a nice addition. Problem's very complex. The great example I give to people when they try to talk about writing generic buffer overflow solutions is airport metal detectors and fingernail clippers. Why do airport metal detectors trigger on fingernail clippers? Well, of course, they're made of metal, but they're not really that malicious. So why do you care? False positives are a big thing. A patch on top of a Band-Aid outside of a bandage wrapped around a cast is not really a great way to fix a problem. They're just layering instead of starting from scratch. Backward compatibility is a big issue. Can you blame anyone for NX not living up to the hype? It's less about programming errors and more about architecture decisions. There's not been a major redesign of the processor architecture you use for 20 years, and there probably won't be for quite some time. Examples shown are not the only ways to avoid the protection. Adopt a layered approach and don't count on a single security solution. For instance, NX plus libc randomization plus API hooking plus host-based IPS plus network-based IPS. At that point, I feel pretty comfortable that somebody can't compromise easily. More research into trusted OS models. You have to sandbox everything. And whatever the future may bring, I assure you, we're going to keep picking it apart. Now that that's over, and it was really short, because my demos were designed to take up a fair amount of time. One of the interesting things are how actually this stuff gets evaluated by the processor, how processor internals. There's been a lot of discussion at this conference about proprietary information being released versus public information and things like that. One of the things that people really should take a look at is how this page table enforcement is being done and how it gets randomly, how it will get randomly enforced. For instance, there's some conditions where, for performance reasons, you don't always want to do a check on the page table entry for execute permissions. Things will run slower. And in a business where you have two major companies competing for speed, you know, the slowest one is going to lose. And it doesn't matter if it's less secure, it just matters if it's slower. So that's an interesting thing to take a look at in the future. Are there any questions? Dan Comiskey.
How would you redesign NX?
Well, I would redesign NX. NX is basically a Band-Aid for a problem. I would redesign the memory architecture as a whole. to better improve separation, segmentation of data in memory between writable memory, between executable code and data and things like that. Basically, I think you have to go back to the drawing board on some of this stuff. Which, for instance, like the Titanium did a lot of that, but nobody really adopted it. So.
Do you think titanium is a fundamentally more secure architecture?
I love Intel. Next question. Speaking of,
Have you noticed differences between the implementations from AMD and Intel? And how are they doing from what you've seen?
it's funny, did anybody see any interesting presentations yesterday? Well, one of the things that were interesting about the presentations yesterday are what you should talk about versus what you know about versus proprietary information. And not that I don't love everybody, and I think that everyone would love that information, but if you start dumping how certain chips do certain things, people might get angry about that. So I would say that fundamentally, from a developer standpoint, XD, the Intel solution, and NX, the AMD solution, are almost virtually identical. The differences get into more microcode issues. Yes, sir.
So maybe I missed your point here. So the no execution feature is not available on the 32-bit Intel?
It's currently not. Basically, in order to have hardware enforced buffer overflow protection, currently right now you can't do it. Unless I'm mistaken, AMD and Intel are both releasing chips soon that will do it on the straight 32-bit platform. But you have to have PAE enabled to do that, basically to make the page table entries wider so you can have more information in them. I think that's coming soon. I'm getting a guy shaking his head who I feel knows about it. So yeah, it will be coming soon, but right now it's not available on 32-bit chips.
So PAE really is a
Well, it's a switch that basically sits in an operating system that will define how the virtual memory lookups are done. And right now it's done on a two-layer approach. PAE basically will add an extra layer of lookup so you can have more information in a greater page table size.
So if you want to get working on Linux, basically just turn on the CP, you can use stack flag and flag.
Yes, sir. Yes, sir.
To answer the question earlier, are you suggesting we need to go complete non-von Neumann architecture kind of thing, or is it that drastic?
I think that it's drastic simply because backward compatibility is the biggest issue. I mean, if you look at the Itanium versus the Opteron, I mean, I think the Itanium was a far superior chip, but everybody seems to love the Opteron more. And why is that? Because the backward compatibility ability in the Opteron far outweighs the performance ability in the Itanium. So I would do it. If I had a magic switch today, and I were like the if I were like the CEO of Intel, I would try desperately to legislate some sort of change like that. But in reality, no one's going to adopt it. They love backward compatibility. Nobody wants to hear that the 10,000 line custom apps they have all over the place in their businesses suddenly have to be rewritten. So I don't think it's going to happen, but I would advocate fleeing von Neumann. Mr. Comiskey again.
How does the software-based step work?
Software-based step works on both 32 and 64-bit versions of chips. Basically, all it does is uses something called safe SCH, safe structured exception handling, to make sure that when an exception happens and code's going to get run, make sure that code is actually a legitimate exception handler and not, for instance, an overwrite from a hacker. It does that by checking the permissions on the page that it's in and where actually it's located.
As an attacker, is software-based step relevant?
No. No, it's only relevant if you like SCH tricks, and I don't really ever do those, so it's never really slowed me down. Any other questions?
What about I mean, I know this is a different subject, but do you consider DLL rebasing a more realistic mechanism for avoiding exploits?
It's funny you mention that. Yes, I do. I think the annex is not a great solution, but I think that it's a step in the right direction. I think if you were to combine it with a form of DLL rebasing at every load, then the potential exploit vectors are mostly all gone, except for the fact you can still do arbitrary overwrites with no problems.
Do you think Sigwin should patch their loader anyway?
I think they already have, actually. I think the version that this was tested on was released in October of last year. I think that since then, the loader's become more annex aware. I haven't had a chance to check that before the show, but that does seem, that's one of the holes right now on our paper. We don't want to say that Sigwin's not doing something. And the point of that wasn't to show that Sigwin has a problem. It was supposed to demonstrate that anything other than a 132 loader that doesn't adhere to their standards has a problem.
How many non-standard loaders are there?
Tons. For instance, IDA has one. Software Ice has one. Most every debugger in the world has one.
But I mean non-debuggers in everyday use. Like if I launch something with packaging with AS Packer, one of the compressing things, are they going to have broken loading?
Well, they have broken loading to begin with. I mean, the loader is very loose about what it will allow to execute. So most, by the generic terms, everything that's packed is broken when it's loading. Any other questions, Mr. Kaminsky? Are you sure? Any other questions? All right, thank you for coming.